What if an entire planet has been waiting in plain sight, glowing above you for your entire life, and you've never really met it? Not the headlines, not the sci-fi myths, not the red blur in a telescope, the real Mars. Tonight, we're going to move past the dramatic stories and the quick summaries. Instead, you'll slowly get to know Mars for what it actually is, why it shines red in the night sky, how long its days stretch, what carved those enormous canyons, how its atmosphere thinned over time, and what it will truly take for humans to one day stand on its surface. As the hours unfold, Mars won't feel like a distant symbol anymore. It will feel like a real place, with its own gravity, its own seasons, its own storms, its own long history written in dust and stone, and maybe eventually a small piece of our future too. Mars is the fourth planet from the Sun, resting in the quiet space between the warmth of Earth and the cold immensity of the outer solar system. If you were to place the planets in a row like lanterns along a long dark road, Mars would be the fourth light you pass, a dim reddish glow that flickers with a strange familiarity, as though it has always known you were coming. It does not blaze with the brilliance of Venus, nor does it carry the sheer enormity of Jupiter. Mars is something subtler. It is a world of middle distances, of in-between places, hanging in the sun's reach, where the warmth is enough to dream of water, but not quite enough to keep it. And in that beautiful, aching middle distance, it has spun its story for billions of years. A single day on Mars, what scientists call a sol, lasts 24 hours and 37 minutes. It is almost the same as a day on Earth. Almost. There is something deeply tender about this small difference, this extra half hour that Mars holds onto like a secret. If you were standing on the Martian surface and watching the pale sun rise and set, you would feel the rhythm of the day in your bones the way you feel it here. Mornings that unfold slowly, afternoons that breathe, and evenings that soften into long blue-tinted twilight. That extra 37 minutes would be yours, every single soul. A quiet gift of time, a little more darkness to rest in, a little more stillness before the next thin, cold dawn arrived to wash the rust-colored hills in pale gold. A year on Mars lasts 687 Earth days, nearly double the length of our own year. To live a Martian year would be to watch the seasons turn in long, slow movements, like the pages of a very old book being turned by an unhurried hand. Each season on Mars stretches out across months rather than weeks, the planet tilting gradually toward the Sun and then away again in a rhythm that is ancient and patient beyond imagination. Imagine celebrating a birthday only once every nearly 2 Earth years. Imagine watching a single summer, thin and cold as it is, linger across the sky for what would feel like an eternity. Mars does not rush its years. It counts them slowly, the way the oldest things count, one long breath at a time. Mars has 2 moons, Phobos and Deimos, and their names carry the weight of ancient myth. Phobos means fear, and Deimos means dread, both drawn from the companions of Ares, the Greek god of war. Yet despite their fearsome names, these 2 small moons are anything but terrifying. They are modest, irregular little worlds, more like tumbling stones than the grand silver sphere that hangs above our own nights. They were not born from Mars the way our moon was born from Earth. Instead, they are thought to be wanderers, ancient asteroids pulled in from the belt between Mars and Jupiter, captured by the planet's gravity long ago and held there ever since in a gentle, endless orbit. 2 small companions in the dark, faithful and unhurried, circling their red world for billions of years. On average, Mars rests approximately 142 million miles from the Sun, a vast and quiet distance that the light of our star crosses in about 12.5 minutes. Think of that for a moment. The same sunlight that falls warm and golden on your face in the morning takes over 12 minutes to reach the red plains of Mars, traveling across an ocean of space so immense that the human mind can only hold it in metaphor. By the time that light arrives, it has thinned just a little, softened just enough that the Martian afternoon is perhaps half as bright as a cloudy day on Earth. And yet the sun still rises on Mars every sol, still draws long shadows across the ancient craters and valleys, still touches the iron-red dust with something that almost resembles warmth. Mars has a diameter of about 4,212 miles, roughly half the diameter of Earth. It is a smaller world, quieter in its proportions, and there is something almost intimate about its size. If you could hold Mars and Earth side by side the way you might hold two stones in your open palms, Earth would be the heavier stone, the fuller one, thick with ocean and cloud and the noise of billions of lives. Mars would be lighter, smoother, worn down by time and silence into something leaner and more still. Yet smaller does not mean lesser. Within those 4,000 miles of diameter, Mars holds the tallest volcano in the solar system, the deepest canyon, ancient river valleys, polar ice caps, and dust storms that swallow entire hemispheres. It is a small world that has never stopped being extraordinary. The gravity on Mars is 38% of Earth's gravity, meaning that if you weighed 100 pounds standing here on Earth, you would weigh only 38 pounds on Mars. Imagine that for a moment. Imagine the lightness of it. You would walk differently on Mars, each step lifting you a little higher than expected, your body rising and falling in a slow, dreamlike rhythm that would feel more like gliding than walking. Heavy things would feel manageable. The simple act of lifting your arms would carry a different quality, a buoyancy you could not quite name. Scientists designing missions to Mars must account for this gentler pull in everything from how astronauts move to how dust falls and how volcanoes grew to be so impossibly tall. Mars holds its world more loosely, more lightly, like a thing that was never quite finished being let go. Mars is the second smallest planet in our solar system, surpassed in smallness only by Mercury, that ancient, cratered world closest to the Sun. In the family of planets, Mars is among the quieter siblings, not the smallest, not the largest, simply somewhere in that gentle middle territory where things are never quite what they first appear. Its size has shaped everything about it, the thinness of its atmosphere, the ease with which its ancient magnetic field faded away, the way its volcanoes grew tall rather than wide because the crust barely moved. Every aspect of Mars, the cold, the dust, the silence, is in some way a consequence of that modest size, a world that had just enough gravity to hold a story together, but perhaps not quite enough to keep all of it from slowly drifting away into the dark. Mars rotates on an axial tilt of 25.19 degrees, remarkably close to Earth's own tilt of 23.5 degrees. This near mirroring is one of the most quietly astonishing coincidences in our solar neighborhood, as though Mars and Earth are two instruments tuned to nearly the same note in a vast and otherwise silent orchestra. It is this tilt that gives both worlds their seasons, the slow, graceful lean toward the sun and then away from it, the warming and the cooling, the lengthening of shadows in winter and their shortening in summer. On Mars, those seasons are longer and more extreme, painted across a landscape that cannot soften them with ocean or forest. But the underlying rhythm is the same ancient tilting dance that Earth has always known, playing out now in iron and ice and rust-colored silence. Because of that axial tilt, Mars experiences 4 seasons, just as Earth does: spring, summer, autumn, and winter, cycling through in their slow Martian way across a year that lasts nearly 2 of ours. The seasons on Mars are not gentle. Spring brings thawing ice and wild dust. Summer is brief and thin-aired and cold by any earthly measure. Autumn watches the dust settle and the temperature begin its long, patient fall. And Martian winter is a deep and silent thing, temperatures plunging low enough to freeze carbon dioxide right out of the atmosphere itself, dusting the poles in dry ice that glitters in the pale, distant sunlight. And yet, despite all the harshness, there is something profoundly familiar about those seasons turning. A reminder that Mars, strange as it is, moves to rhythms we were born already knowing. Olympus Mons is the tallest volcano in the entire solar system, rising approximately 13.6 miles above the Martian surface, nearly 3 times the height of Mount Everest measured from Earth's sea level. To look upon Olympus Mons from space would be to see a thing so vast that it barely looks like a mountain at all. Its base spreads across 370 miles, wider than the entire state of Arizona, and its slopes rise so gradually that if you were standing somewhere in the middle of it, you would not know you were on a volcano. The horizon would simply curve away from you in all directions, and the summit would be far, far above the visible edge of your world. It grew so tall because Martian gravity is lighter and the crust barely moves. The same volcanic hotspot feeding the mountain for billions of years, building it skyward in patient, magnificent silence. Valles Marineris is a canyon system stretching roughly 2,500 miles along the Martian equator, nearly as wide as the entire contiguous United States measured from coast to coast. It is not a single canyon, but a vast network of interconnected chasms, rifts, and valleys that spread across the planet like the cracked, drying skin of something immeasurably old. The Grand Canyon on Earth, that breathtaking American landmark carved by the Colorado River over millions of years, could fit inside one of Valles Marineris' smaller tributaries and almost disappear. Scientists believe this enormous system was not carved by water but by the tectonic forces of the planet itself, the crust pulling apart along ancient fault lines over billions of years, opening slowly the way a long-held breath is finally released, gradually, then all at once, and then settling into a silence that has lasted ever since. In some places, Valles Marineris plunges nearly 7 miles deep into the Martian crust, a depth so profound that if you stood at the bottom and looked up, the canyon walls would tower above you like the walls of a world, and the thin strip of pink Martian sky would feel impossibly far away. 7 miles. The deepest point in Earth's ocean, the Challenger. Deep in the Mariana Trench, is about 7 miles down from the surface of the sea. To stand at the bottom of Valles Marineris would be to feel that same staggering depth, except rather than water pressing down around you, there would be silence. Ancient, carved stone silence. Layers of rock on either side that read like the pages of a 4-billion-year-old book, each stratum a chapter in the story of a world that is still, even now, only partially understood. The surface of Mars is covered in iron oxide, rust, and it is this rust that gives the planet its iconic red color, the color that has drawn human eyes skyward for thousands of years and filled our myths with war and fire and divine presence. The redness of Mars is not a trick of the light or a property of its atmosphere alone. The ground itself is red. The dust is red. The fine particles suspended in the Martian air are red, drifting and settling and lifting again in red curtains across red plains under a sky tinted orange and pink and butterscotch. Somewhere in the ancient past, Mars was wet enough for oxygen and iron to combine, for rust to form in the slow, elemental way that rust always forms, and then the water vanished and left the rust behind, a planet painted in the color of something that once burned and was never quite extinguished. Mars has the largest dust storms in the entire solar system. Storms so vast and so powerful that they can envelop the entire planet in a veil of swirling red dust that blocks the sun and turns the world into a dim ochre twilight for months at a time. On Earth, our largest sandstorms are local events, regional curtains of dust that pass through and leave. On Mars, a storm can begin in one small region, feeding on the heat generated by the dust it raises, growing and spreading outward until there is no corner of the planet untouched by it. The rovers that have worked on the Martian surface have had to wait out these storms in silence, their solar panels starved of light, their instruments powering down to the barest minimum, simply enduring, like a creature that knows winter is coming and settles in to outlast it. These global Martian dust storms can last for months at a time, weeks and weeks of the planet wrapped in its own particulate veil, the surface hidden from the sky and the sky hidden from the surface in one long, unbroken amber twilight. It was such a storm that ultimately silenced the Opportunity rover in 2018 after nearly 15 years of faithful exploration. The dust thickened, the sunlight thinned, and Opportunity's solar panels could no longer gather enough energy to keep the rover's systems warm through the Martian night. Scientists sent signal after signal, over 1,000 attempts to reach the rover across the months that followed the storm's clearing. But Opportunity never answered again. It had simply grown too cold, settled into the Martian dust, and gone quiet. The storm that ended it had been just the planet breathing in its deep, slow, ancient way. The North Pole of Mars is home to a permanent ice cap made of water ice, a layered, luminous disk of frozen water and dust that stretches roughly 600 miles across and rises in places to nearly 2 miles above the surrounding plains. It does not melt away entirely in summer the way the South Polar Cap's outer layers do. It persists, enduring, a white and quietly gleaming monument to the water that Mars once held in such abundance. Scientists who study this ice cap have found that it holds enough water, if melted, to cover the entire planet in a shallow sea, not deep, but real, actual liquid water in quantities that speak to Mars's wetter past. That ice sits there now in the northern darkness, patient and cold, holding the memory of Martian oceans in every crystalline layer, as though the planet itself has not quite decided to forget. The South Pole of Mars hosts a different kind of ice cap, one made mostly of dry ice, which is frozen carbon dioxide rather than water. In the depths of Martian winter, carbon dioxide from the atmosphere freezes out and settles on the southern pole in layers that can be several feet thick, turning that region of the planet into a strange, glittering expanse of frozen air. Come Martian spring, the dry ice sublimates, passing not from solid to liquid but directly from solid to gas, and carbon dioxide breathes back into the atmosphere in great invisible exhalations, as though the planet were slowly waking up and sighing. Beneath the dry ice, there is also a permanent layer of water ice, quieter and more lasting. The two poles of Mars together hold the planet's remaining water in frozen custody, guardians of a resource that may one day matter enormously. Etched into the surface of Mars are the channels and valleys of rivers that have not flowed for billions of years, ancient riverbeds carved into the rock when Mars was young and wet and possibly alive with the conditions that life requires. From orbit, these channels look unmistakable, long branching paths that narrow upstream and widen downstream that curve the way rivers always curve, following the gradient of the land with the patient logic of flowing water. They speak of a time when rain may have fallen on Mars, when streams gathered into rivers and rivers gathered into lakes and perhaps something even larger. That time is unimaginably long past. The water is gone, locked in ice, lost to space, hidden underground. But the shapes it carved are still there in the stone, permanent as memory, older than anything alive. The Hellas Planitia impact basin is one of the largest impact craters in the solar system. Approximately 1,400 miles wide and nearly 5 miles deep, a scar left on the southern hemisphere of Mars by a collision so enormous that it reshaped the planet's landscape in a single cataclysmic moment billions of years ago. To stand at the rim of Hellas and look inward would be to gaze across a depression so vast that weather forms differently inside it. The atmospheric pressure at the basin floor is higher than almost anywhere else on Mars, and temperatures inside are slightly warmer than the surrounding terrain. Scientists have speculated that if Mars were to be terraformed one day, Hellas Planitia might be among the first regions where liquid water could pool, where the air could be breathed, where the first tentative steps of an alien spring might take root in ancient, crater-carved soil. Mars has an atmosphere that is extraordinarily thin, about 1% the density of Earth's, and this thinness shapes everything about the planet's character. On Earth, our atmosphere is a thick, living blanket, holding warmth, carrying sound, distributing water, protecting the surface from the harshest radiation of the sun. On Mars, the atmosphere is more like a whisper than a blanket, present, but barely. A veil of gas so thin that standing on the Martian surface without a pressurized suit would be something like standing at 3 times the altitude of Mount Everest's peak, where the air is too thin to sustain a breath. And yet that thin atmosphere does something. It carries dust, it shapes weather. It holds the planet's carbon dioxide in a slow and seasonal cycle. It is not nothing. It is a thin and quiet breath, the breath of a planet that was once far fuller and has been slowly exhaling ever since. The Martian atmosphere is composed of approximately 95% carbon dioxide, the same gas that plants on Earth exhale and breathe in reverse, the same gas that is slowly warming our own planet's atmosphere in quantities far, far smaller than what Mars holds. On Mars, the prevalence of carbon dioxide is not a sign of industrial excess or ecological imbalance. It is simply what was left when everything else, the water vapor, the oxygen, the nitrogen, was stripped away over billions of years by the slow loss of Mars's magnetic field and the persistent reach of the solar wind. What remains is a cold, thin carbon dioxide atmosphere that freezes at the poles in winter and evaporates in spring, cycling with the seasons in a rhythm that has no life to observe it and no lungs to breathe it. Only the planet itself turning quietly in the dark, cycling its cold air from pole to pole like a patient, sleeping thing. Nitrogen makes up about 2.6% of the Martian atmosphere, a small fraction, but significant. On Earth, nitrogen is the dominant component of our air, filling about 78% of every breath we take. It is the silent background note in the chord of our atmosphere, not directly breathable but essential for life as we know it, a key ingredient in proteins and DNA and the chemistry of living things. On Mars, nitrogen is present in only a whisper, not enough to sustain Earth-like biology, but enough to represent a resource that future human settlers might want to utilize. Scientists who dream of one day making Mars more hospitable for human life know that this thin sliver of nitrogen would need to be supplemented enormously. But it is there. A small and quiet presence in the Martian air, like a candle flame in a very large and very dark room. The average surface temperature on Mars is approximately -80 degrees Fahrenheit, a cold so profound and pervasive that it is difficult to hold it in the imagination as anything other than abstract. At -80 degrees, metal becomes brittle. Unprotected skin would suffer almost instantaneously. Liquids freeze not gently but completely without hesitation. And yet this is the average, the median of all the days and all the nights across all the latitudes of a world, the temperature of Mars when you blend its warmest equatorial afternoons with its cruelly cold polar winters and arrive at something in the middle. That middle is still a cold most of us will never know. And the cold is not still. It moves with the wind, it settles into the valleys at night. It presses against the thin atmosphere and finds every fissure in the rock and every grain of iron dust and holds them all, gently in its long, unbroken embrace. Near the Martian poles in winter, temperatures can plunge to -220 degrees Fahrenheit, cold enough that the carbon dioxide in the atmosphere begins to freeze and fall to the ground as dry ice snow. It is a cold that exists at the outermost edges of what human technology can measure and survive. A cold that belongs not to weather as we know it, but to something older and more elemental. The cold of space itself, seeping down into the lowest latitudes through the thin atmospheric veil. In these polar winters, Mars becomes one of the most inhospitable places in the known solar system. A landscape of frozen gas and silence so absolute that even the dust storms that sometimes rage across the rest of the planet cannot penetrate. It is the stillest, coldest corner of a world that is already still and cold. A silence within a silence held in permanent glacial darkness. On a warm summer afternoon near the Martian equator, temperatures can briefly climb to around 70 degrees Fahrenheit, a temperature that on Earth would feel like a mild and pleasant day. This is one of Mars's most quietly astonishing qualities. For a few hours, in a few places, on the best days of the Martian year, the planet becomes almost hospitable by temperature alone. Almost. The air is still unbreathable, the pressure still far too low for liquid water to persist, the sky still tinted dusty amber instead of blue. But the temperature says something different. It says warmth. It says the possibility of something like comfort dressed in an alien landscape that has never known a footstep or a spoken word. Those brief equatorial afternoons are Mars at its most approachable, a glimpse of what the planet might have been when it was younger and wetter and perhaps, in its own quiet way, more alive. The thin atmosphere of Mars means the planet cannot retain heat the way Earth does, and this causes temperatures to swing wildly between day and night, sometimes by as much as 170 degrees Fahrenheit in a single sol. On Earth, our thick atmosphere acts as an insulating layer, trapping the day's warmth and releasing it slowly through the night so that temperatures change in gradual, measured ways. Mars has no such insulation. When the thin Martian sun sets and the sky darkens, the heat that spent the afternoon softening the iron dust simply escapes, rising up through the transparent atmosphere and vanishing into space almost instantly. The night that follows is immediate and brutal, the temperature dropping tens of degrees in the first few hours after sunset. It is the cold of a world unswaddled, exposed to the universe in a way that Earth, wrapped in its warm blue blanket of air, has never been. Mars experiences dust devils, spiraling, swirling columns of wind and dust that rise miles into the Martian sky, visible from orbit as dark, wandering marks moving slowly across the rust-colored plains. On Earth, dust devils are small and short-lived, a novelty in desert regions, spinning for a moment and dissolving. On Mars, dust devils can grow to extraordinary sizes, some reaching heights of over 5 miles, towers of spiraling redness stretching from the ground up into the pale Martian atmosphere, moving across the landscape with an eerie, purposeful quality like living things. The rovers exploring Mars have encountered dust devils numerous times, and in some cases these spinning columns have actually done the rovers a favor, sweeping dust from solar panels and restoring their power, an accidental kindness from a planet that otherwise asks for so much endurance. The daytime sky on Mars appears not blue but a soft butterscotch or pinkish tan, a warm and otherworldly palette painted by the fine iron dust particles suspended in the thin atmosphere, scattering the sunlight in ways entirely different from how Earth's thick, water-rich air scatters it. On Earth, shorter blue wavelengths of sunlight are scattered in all directions by the molecules of our atmosphere, which is why we look up and see blue. On Mars, the dust particles are large enough to scatter the longer red and yellow wavelengths, tinting the sky in amber and ochre. To stand on Mars in daylight would be to feel as though you were living inside a painting made of warm, dusty light. The sun smaller and more distant than you are accustomed to, the shadows long and sharply defined, and the horizon glowing in colors that have no name in any human language. At sunrise and sunset on Mars, the sky does something extraordinary. It turns a soft and haunting shade of blue around the sun, the colors reversing themselves into something that feels like Earth seen through a mirror. On Earth, sunsets are warm, orange and red and gold. On Mars, sunsets are cool, blue and violet, a pale ethereal glow that rings the shrinking disk of the sun as it touches the horizon. It is the same physics in reverse. At low angles, the Martian dust scatters the red light away and allows the blue to pass through more directly to the observer's eye. The result is a sunset of extraordinary, melancholy beauty. Every rover that has watched the Martian sun go down has sent back images of this blue twilight. And those images carry a feeling, a quiet, inexplicable feeling, that there is something deeply beautiful about a world that turns its warmest colors cold at the end of every day. Phobos is the larger of Mars's 2 moons, though larger is relative because Phobos is still a remarkably small object, measuring only about 17 miles across at its widest point. It is not round the way our moon is round, shaped by the patient pull of its own gravity into a perfect sphere. Phobos is lumpy and irregular, potato-shaped, its surface heavily cratered and grooved, more like an asteroid that was persuaded to stay than a true moon that was born. And yet Phobos has a kind of quiet dignity in its smallness. It orbits Mars closer than any other moon orbits any planet in the solar system, only about 3,700 miles from the Martian surface, so close that it would appear to the naked eye as a visible disk in the Martian sky, moving rapidly from horizon to horizon, a small, misshapen companion rushing endlessly around its red world. Phobos orbits Mars not once but 3 times in a single Martian day, moving so quickly in its close orbit that it actually rises in the west and sets in the east, traveling in the opposite direction from the planet's rotation. This is one of the stranger details in a solar system full of strange details. A moon that appears to run backward across the sky of its parent planet, rising and setting twice before the sol is done. For a visitor standing on the Martian surface and looking up, Phobos would appear briefly as a small, rapidly moving shape. Not the slow and stately traversal of Earth's moon across our own night sky, but something faster and more urgent, crossing from horizon to horizon in just 4 to 5 hours. It would be like watching a clock with a second hand you could actually see against the stars. Phobos is slowly spiraling inward toward Mars, drawn closer by tidal forces, and in approximately 50 million years it will either crash into the Martian surface or be torn apart by the planet's gravity into a ring of debris that will circle Mars for some time before eventually settling. 50 million years is an unimaginable span of time, longer than our species has existed by a factor of tens of thousands. And yet in cosmic terms it is not so very long. The universe is old enough for 50 million years to be a brief chapter, a paragraph in a story that began nearly 14 billion years ago. Phobos does not know it is falling. It simply continues its rapid circles, faithful and unconcerned, as it has always done, as it will do for countless generations beyond our own, slowly descending toward its end in the gravity of the world it has circled since before life learned to walk on Earth. Deimos is one of the smallest known moons in the entire solar system, measuring only about 9 miles across, smaller even than some of the larger asteroids drifting through the belt between Mars and Jupiter. It is a tiny, quiet thing, orbiting so far from Mars compared to Phobos that it moves in a more leisurely rhythm, its surface even more battered and ancient-looking, its shape even more irregular. Deimos does not have the dramatic future that Phobos has. It is not spiraling inward to its eventual destruction. Instead, its orbit is slowly expanding outward, and in the distant future it may drift away from Mars entirely, escaping the planet's gravity and returning to wander the solar system as an unattached asteroid once more. A moon that was never truly at home, perhaps, only briefly staying before resuming its journey through the dark. Deimos takes approximately 30 hours to complete one full orbit around Mars, just a little more than one Martian sol. From the surface of Mars, Deimos would appear to rise in the east and set in the west, like the sun itself, moving so slowly across the sky that it would seem almost stationary. An observer with patience might watch it for 2 or 3 nights in a row, barely noticing its movement against the background of stars. There is something deeply peaceful about this, the tiny moon's slow, unhurried circuit of its world, taking its time where Phobos rushes, drifting where its sibling moon hurries. If Phobos is a heartbeat, quick and close and urgent, then Deimos is a long, slow breath, a small and distant light moving with the quiet certainty of something that has nowhere it needs to be. Both Phobos and Deimos are thought to be captured asteroids, ancient rocks from the belt between Mars and Jupiter that wandered too close to Mars billions of years ago and were caught in its gravity, persuaded to stay as moons by the quiet insistence of orbital mechanics. This theory is supported by their composition, which appears similar to the carbonaceous asteroids found in the outer regions of the belt, and by their irregular, unspherical shapes, which suggest objects that never had enough mass for gravity to pull them into roundness. The idea of a captured moon carries something poignant in it. The image of a wandering stone traveling alone through the solar system for billions of years, then gradually finding itself pulled into a new relationship, a new orbit, a new sky to look down from. Captured, yes, but held too, and still there, after all this time. Phobos bears on its surface a massive crater called Stickney, named for the wife of Asaph Hall, the astronomer who discovered both Martian moons in 1877. Stickney is about 6 miles wide, nearly a third of the diameter of Phobos itself, and the impact that created it must have come perilously close to shattering the small moon entirely. When scientists study the crater, they can see that the impact sent shockwaves through Phobos in all directions, leaving long grooves and striations across much of the moon's surface, cracks in the stone that radiate outward from Stickney like the lines from a spider's web. The grooves are still visible today, 4 billion years later, a record of an ancient collision preserved in the airless, unchanging cold of a world too small to erase its own scars. Phobos wears that wound still, quietly, as old things tend to do. From the surface of Mars, Phobos rises and sets twice in a single Martian day, and because of its rapid westward movement across the sky, a watcher on the Martian surface would see it rise in the west and trace its path across the sky in just 4 to 5 hours before it disappears below the eastern horizon. There is something almost hypnotic about this, the image of a small, irregular moon moving backward against the natural direction of the other lights in the sky. The stars drifting one way in their ancient, patient courses while Phobos hurries the other way, urgent and peculiar, a small anomaly in the otherwise ordered darkness. Ancient sky watchers on Earth, had they been given such a moon, might have given it a different name than fear. They might have called it the rushing one, or the moon that runs. From the surface of Mars, Deimos appears as little more than a bright star, a point of light in the Martian night sky, barely distinguishable from the actual stars behind it by anything other than its slow, steady movement across the field of view. There is no disk visible, no shadowed face, no sense of dimension, just a small, bright point moving with gentle patience through the darkness. If you did not know to look for it, you might not recognize it as a moon at all. And there is something quietly beautiful about that smallness. A moon so far from its planet, so small in its orbit's scale that it has barely been noticed in the grand sweep of the solar system. Deimos persists anyway, that little light, faithful and unassuming, circling its red world in the dark for billions of years, seen or unseen, whether anyone is watching or not. Neither Phobos nor Deimos is large enough to produce a total solar eclipse as seen from the Martian surface. They can only create partial eclipses, passing across the face of the sun as small, dark shapes that block only a portion of the light. The rovers on Mars have actually photographed these events, small potato-shaped silhouettes sliding slowly across the disk of the sun, the light dimming only slightly, the landscape not plunging into the dramatic totality that Earth experiences during its own lunar eclipses. There is something humbling about a partial eclipse, a reminder that the universe does not always deliver the grand gesture. Sometimes it offers only the small and the incomplete, the moon that is not quite big enough, the darkness that is not quite total, the beauty that is quiet and partial and real. The first successful Mars flyby was achieved by NASA's Mariner 4 spacecraft in 1965, a sleek scientific vessel that spent 8 months traveling the vast distance between Earth and Mars before skimming past the planet at about 6,000 miles, close enough to photograph but not close enough to land. Mariner 4 was not large. It was not glamorous. It was a collection of instruments and antennas and solar panels assembled by human hands and launched on a trajectory calculated by human minds, sent across an ocean of space with the quiet ambition that has always characterized our species at its best. When Mariner 4 flew past Mars, it took 22 photographs, grainy, black and white images that nonetheless showed something no human eye had ever truly seen before: the real surface of another planet, close enough to count its craters. Mariner 4's flyby returned the first close-up photographs ever taken of another planet from space. And those photographs, when scientists processed them and gathered around to look, revealed a surface far more ancient and cratered than many had hoped. Before Mariner 4, some scientists and many dreamers had imagined that Mars might be more Earth-like, that the canals some observers thought they saw from Earth might prove to be real, that life might be not so different from home. The images said otherwise. They showed a cold, cratered, ancient landscape, a world that had been still for a very long time. For some, those images were a kind of mourning for a Mars that had never been. But for others, they were the beginning of a deeper love, a love for what Mars actually is, in all its cold, magnificent, honest reality. On July 20th, 1976, exactly 7 years after the Apollo 11 moon landing, NASA's Viking 1 lander successfully touched down on the surface of Mars, becoming the first spacecraft to land on Mars and operate successfully for an extended period. The landing itself was a moment of extraordinary tension. The spacecraft had to execute a complex automated sequence, slowing from its orbital velocity, deploying a parachute, firing retro-rockets, and lowering itself to the ground in an entirely automated process with no possibility of human intervention. A dance with physics and distance that took place in silence, the results not known on Earth until after they had already occurred. When the signal came back confirming a successful landing, the rooms full of scientists exhaled as one, and Mars was never quite the same again. Viking 1 returned the first color photographs from the surface of Mars, and those images showed a world of extraordinary russet beauty. The reddish-brown soil stretching away to a salmon-colored sky, rocks scattered across the plain in the casual way that nature always arranges its objects, as though the landscape had simply always been that way and was not expecting company. Scientists had debated what color the Martian sky would be. Some expected blue. The first images, quickly processed, seemed to show a blue sky, and this caused a brief excitement before calibration revealed the truth. The sky was not blue, but a soft, dusty pinkish amber, colored by the ever-present iron dust that hangs in the thin atmosphere. The real color of Mars, it turned out, was reddish all the way from the ground to the top of the sky, a world wrapped in its own particular shade of rust and wonder. NASA's Mars Pathfinder mission landed on Mars on July 4, 1997, carrying with it the first Mars rover, a small six-wheeled vehicle named Sojourner after the abolitionist and women's rights activist Sojourner Truth. The mission was, in many ways, a test. Could a rover be designed, built, and successfully operated on another planet? Could the software handle the unexpected terrain, the communication delays, the unpredictable surface? The answer, it turned out, was yes. Sojourner rolled off its landing platform, trundled across the Martian soil, examined rocks and soil with its instruments, and sent back data that delighted the scientific community. It was small and it was slow, and it was not on Mars for very long, but Sojourner opened a door that has never been closed, the door to exploration by wheel on another world. Sojourner was approximately the size of a microwave oven, small enough to have fit comfortably in your kitchen, modest enough to have been overlooked in a room, and yet powerful enough to carry humanity's scientific curiosity across 60 million miles of space and roll it slowly across the surface of another world. There is something almost tender about Sojourner's smallness. It was not an imposing machine. It weighed only about 23 pounds, about the weight of a toddler, and its top speed was roughly 1 inch per second. And yet it examined the mineralogy of Martian rocks for the first time. It transmitted hundreds of images. It made its way through a landscape no machine had ever navigated before, one careful, unhurried inch at a time. Small things, done with great patience across great distances, can still change everything. In January of 2004, NASA landed 2 twin rovers on opposite sides of Mars, Spirit in the Gusev crater and Opportunity in the Meridiani Planum. They arrived weeks apart, both bouncing to a halt inside airbag-cushioned landing shells before unfolding themselves on the ancient Martian surface and beginning to work. Spirit and Opportunity were not identical twins in experience. Spirit drove across rocky highland terrain, found evidence of volcanic activity and water-altered minerals, and eventually became immobilized in soft sand in 2009, working in place until communication was lost in 2010. Opportunity had a different journey. A longer one, a more extraordinary one. Together they became the foundation of modern Mars surface science, transforming what had been orbital observations into ground truth, wheel tracks, and direct chemical measurements of a world that had waited billions of years for any of this. Opportunity was designed to last 90 days and ended up operating for nearly 15 years, one of the most extraordinary records of mechanical endurance and scientific performance in the history of space exploration. It drove more than 28 miles across the Martian surface. It discovered hematite spheres nicknamed blueberries that formed in the presence of water. It survived a global dust storm in 2007. It explored the crater Victoria and the vast Endeavour crater. And then, in the summer of 2018, another global dust storm arrived, and this time the dust was too thick, the solar panels too starved of light, and Opportunity fell silent. NASA's last communication from the rover contained a message that a team member read from the final telemetry data. "My battery is low and it's getting dark." A quiet ending for a machine that had given everything it had. NASA's Curiosity rover landed in Gale Crater on Mars in August of 2012 and has been exploring ever since. A nuclear-powered, car-sized laboratory that has traveled more than 18 miles across the Martian surface and conducted thousands of scientific experiments in the years since its arrival. Curiosity was larger than anything that had come before it, descended to the surface via a complex sky crane maneuver that lowered the rover on cables from a hovering rocket-powered platform before the platform flew away and landed at a safe distance. It was an audacious piece of engineering, a machine so large that airbags alone could not cushion its landing, requiring an entirely new solution built from imagination and mathematics and the particular human refusal to accept that something cannot be done. Curiosity found organic molecules on Mars. It found evidence of ancient habitable lake environments. It climbed a mountain. It is still climbing. The Perseverance rover landed in Jezero Crater on February 18, 2021. The most advanced Mars rover ever built, carrying 17 cameras, 2 microphones, and a suite of scientific instruments designed specifically to search for signs of ancient microbial life. Perseverance also carried a small helicopter named Ingenuity tucked beneath its belly, a technological experiment that would go on to make history of its own. The landing brought tears to the eyes of engineers at NASA's Jet Propulsion Laboratory, not only because the landing succeeded, but because it succeeded during a global pandemic, with most of the team working remotely, communicating across screens, unable to share the same room for the celebration they had worked years to earn. And yet the rover landed perfectly, its cameras awakening to the broad, ancient delta of Jezero, and it began immediately the work of listening for life in the stone. Scientists believe that Mars once had liquid water flowing across its surface billions of years ago, not just in small quantities, but potentially in rivers and lakes, and perhaps even a shallow ocean covering much of the northern hemisphere. This is not speculation alone. The evidence is written in the rock: ancient riverbeds carved by flowing water, sedimentary layers deposited over millennia in lake environments, minerals that only form in the presence of liquid water, chemical signatures that speak of a wet past with a specificity that leaves little room for doubt. Mars was not always the dry, frozen red desert it is today. Once it was something else, something warmer, something wetter, something that may have held, in the right conditions, in the right places, in the right seasons, exactly the chemical conversations that life requires to begin. Evidence of ancient lake beds has been found in multiple regions of Mars. Flat, layered deposits of sedimentary rock that speak of still water, of slow sedimentation, of centuries of quiet accumulation in basins that were once filled with liquid that is now long gone. Lakes, if they existed on Mars for long periods, would have been among the most hospitable places on the young planet for the emergence of life, sheltered from the worst of the radiation, filled with minerals dissolved from surrounding rock, potentially warmed from below by geothermal heat. The layers in these ancient lake beds are being studied with the same care that geologists study the strata of Earth's ancient seabeds, reading time in stone, reading chemistry in color, looking for anything that speaks of the presence of carbon, of organic chemistry, of the building blocks that life has always reached for first. The Jezero crater, where the Perseverance rover landed, is believed to be the site of an ancient lake delta, a place where a river once flowed into a standing body of water, depositing layer upon layer of sediment over millions of years in a fan-shaped formation that is still visible from orbit, still readable as a geological story written in the shape of the land. Deltas on Earth are among the richest environments for the preservation of ancient life. The sediment traps organic material, buries it and protects it from the erosion and chemistry that would otherwise destroy it. Scientists chose Jezero specifically because it offers what may be the best possible chance of finding preserved biosignatures, the chemical fingerprints of life, if life ever existed there. Perseverance is currently climbing the delta's edge, drilling and sampling, listening to the stone for an answer that may take decades to hear clearly. Mars has confirmed deposits of water ice beneath its surface in multiple regions, not just at the poles where ice caps are visible from orbit, but buried under the soil in mid-latitude regions, hidden below a thin layer of dust and regolith that protects the ice from sublimating directly into the atmosphere. This subsurface ice was detected by radar instruments on orbiters, confirmed by the Phoenix lander in 2008, which actually scraped the surface and exposed the ice directly. These buried ice deposits are significant not only as scientific evidence of Mars's watery past, but as a potential resource for future human exploration. Water that could be extracted, purified, used for drinking, for growing food, for producing rocket propellant through electrolysis. Mars is not as waterless as it appears. The water is simply underground now, patient and frozen, waiting in the dark for whatever comes next. In 2018, radar data from the Mars Express orbiter suggested the possible presence of a liquid water lake buried roughly 1 mile beneath the southern polar ice cap, a finding that sent excitement through the scientific community and sparked debates that continue to this day. The radar signals that suggested liquid water were compelling, a bright, reflective layer beneath the ice, consistent with the kind of signal that liquid water would produce. But more recent studies, published between 2021 and 2023, have raised important questions about this interpretation, suggesting that the same radar signals might be caused by clays, volcanic rock, or other geological features rather than liquid water. The question remains beautifully unresolved, a mystery still turning in the dark beneath 1 billion tons of ancient ice. Whatever is down there, water or stone or something not yet imagined, it is still waiting to be understood. The search for life on Mars focuses not on complex organisms, not on creatures that move or breathe or think, but on microbial life, single-celled organisms of the kind that were the only life on Earth for the first 2 billion years of our planet's history. Microbes are extraordinarily resilient. They have been found in acid hot springs and Antarctic ice and the crushing depths of the ocean and the interiors of nuclear reactors. They are, in many ways, the hardiest form of life we know. And if Mars was once warmer and wetter for long enough, microbes might have had not just the opportunity but the time to emerge. Whether they still exist today, perhaps underground, near geothermal heat, near liquid water, or whether they existed only in the distant past and left only chemical traces behind, is the central question of Martian astrobiology. It is perhaps the most important question our species has ever asked of another world. In 1976, NASA's Viking landers conducted the first biology experiments ever performed on another planet, a suite of tests designed to detect signs of biological activity in the Martian soil, and the results were, and remain, a source of scientific debate. One of the experiments, the labeled release experiment, actually produced a positive result. A gas was released from the soil that looked initially as though something biological might be responsible. But the other experiments did not support the presence of organic molecules, and the scientific consensus settled on a chemical explanation rather than a biological one, the result of highly reactive perchlorate chemicals in the Martian soil rather than microbes. And yet the debate was never entirely closed. The results remain inconclusive, not impossible, not confirmed, just inconclusive. A word that, in the context of searching for life on another world, carries an enormous amount of weight. Methane has been detected in the Martian atmosphere in what appear to be seasonal fluctuations, and methane is a molecule that, on Earth, is most commonly produced by living organisms, by decomposing organic matter, by the metabolic processes of microbes in wetlands and soil and the intestines of animals. The detection of methane on Mars does not prove that life exists there. There are non-biological sources of methane, volcanic activity, the reaction of water with certain minerals in a process called serpentinization, and any of these could explain the Mars observations. But the seasonal fluctuation of the methane signal is harder to explain through purely geological means, and Curiosity's on-the-ground detections of methane spikes have only deepened the mystery. It remains one of the most intriguing open questions in planetary science, a single molecule, present or absent, that carries the weight of everything. The Perseverance rover is collecting rock and soil samples from Jezero crater and sealing them inside small titanium tubes, depositing them on the Martian surface for eventual retrieval by a future sample return mission, a collaborative effort between NASA and the European Space Agency that aims to bring Martian material back to Earth for analysis in laboratories far more sophisticated than anything that can currently fit inside a rover. The science that could be done on those samples on Earth, with electron microscopes and mass spectrometers and techniques not yet invented, could answer questions that no rover instrument will ever be equipped to answer in the field. The samples are waiting on Mars now, sealed in their tubes, lying on the rust-colored ground in the ancient delta of Jezero, patient as the planet itself, waiting for the day a mission arrives to carry them home across the dark. Mars's current environment, dry, frozen, irradiated and crushed under a thin atmosphere with less than 1% of Earth's pressure, makes it extraordinarily hostile to life as we know it today. The surface is bathed in ultraviolet radiation, since Mars has no magnetic field to deflect the solar wind and no thick ozone layer to filter the incoming radiation. Liquid water cannot exist on the surface. It would immediately freeze, boil, or both, depending on temperature, in an atmosphere too thin to keep it stable. And the perchlorate chemicals that saturate the Martian soil would be toxic to most Earth-based biology. And yet, in the same breath that science names these obstacles, it reminds us that Earth itself was once similarly hostile, that life has arisen under conditions that once seemed impossible, and that the universe has a habit of finding ways where our imaginations have built walls. Mars has no global magnetic field today, unlike Earth, which is surrounded by a vast, invisible magnetosphere generated by the movement of molten iron in its outer core, a protective bubble that deflects the charged particles of the solar wind and shields the surface from their effects. Mars lost its global magnetic field billions of years ago, and the consequences of that loss were enormous and slow and irreversible. Without the magnetic field, the solar wind, that constant stream of charged particles flowing outward from the sun, began to strip away the Martian atmosphere molecule by molecule over billions of years. The planet grew thinner, the pressure dropped, the water could no longer stay liquid, and Mars became, gradually, over unimaginable spans of time, the cold and quiet world it is today. The loss of a magnetic field was not a dramatic event. It was the slow closing of a door. Scientists believe that Mars once had a strong global magnetic field, similar to Earth's, generated by the circulation of molten iron in the planet's core, protecting the early Martian atmosphere and potentially sustaining conditions hospitable enough for liquid water and, perhaps, for life. Evidence for this ancient field is preserved in the magnetized rocks of the oldest Martian terrain. The southern highlands, which are among the most ancient surfaces in the solar system, bear magnetic stripes baked into them during the era when the field was active. Then, something happened. The core cooled. The convection that drove the dynamo stopped, and without the engine that generates a magnetic field, the field itself simply faded away, leaving Mars unshielded and vulnerable in ways that would take hundreds of millions of years to fully manifest. The ancient field is gone, but it left its memory in the stone. Without a global magnetic field, Mars is continuously bombarded by solar radiation, the high-energy particles and cosmic rays that the Sun and the broader galaxy send streaming through the solar system in endless, invisible torrents. On Earth, these particles are largely deflected by our planet's magnetosphere, channeled toward the poles where they produce the aurora borealis and australis, those shimmering green and violet curtains of light that are, in fact, the visible consequence of our planet's invisible protection. On Mars, there is no such protection. Radiation reaches the surface directly, penetrating the thin atmosphere with little resistance. Any organism living on the Martian surface today would need extraordinary radiation resistance to survive. Any future human visitors will require shielding from the ground, from regolith mounded above their habitats, from the planet itself piled protectively around them. The loss of Mars's magnetic field is thought to have been the primary driver of the loss of its once thick atmosphere, a process that unfolded over hundreds of millions of years as the solar wind slowly stripped molecules from the top of the Martian atmosphere and carried them away into space. NASA's MAVEN orbiter, which arrived at Mars in 2014, was designed specifically to study this process, and it has measured the current rate of atmospheric loss directly. Mars is still losing its atmosphere today, still thinning, still breathing out into space through the slow leak that began billions of years ago. In the past, when the solar wind was stronger, the loss was faster. Now it is slow, but it is still happening. The planet still exhaling its remaining air at a rate that, given enough time, will leave even less behind than what is already so thin. Mars has a core composed of iron, nickel, and sulfur, a dense, metallic heart at the center of the planet that was once hot enough and active enough to generate the global magnetic field that the young Mars needed to protect its atmosphere and its water. Today, that core is at least partially solidified, its convection slowed or stopped, the dynamo that once powered the magnetic field silent. NASA's InSight lander, which arrived on Mars in 2018, provided the first direct seismic measurements of the Martian interior, helping scientists determine not only the size of the core but its composition and state: partially liquid, denser than expected, rich in sulfur in proportions that help explain why it behaves differently from Earth's more purely iron-dominated core. The heart of Mars, examined for the first time from the inside, turned out to be quietly surprising, as hearts often are. NASA's InSight lander detected Mars quakes for the first time in 2019, seismic events on Mars that ripple through the planet's interior and allow scientists to map its internal structure the same way a doctor uses sound waves to image the body. Marsquakes are not like large earthquakes. They are much smaller, more subtle, more like distant whispers in the rock than the thunderous upheavals that shake buildings on Earth. Mars is not as seismically active as Earth, and without active plate tectonics, the quakes tend to be caused instead by the cooling and contracting of the planet's interior or by impacts. But each quake, however small, carries information about the thickness of the crust, the properties of the mantle, the state of the core. InSight listened to the planet's heartbeat for over 4 years before its solar panels became too dust-covered to sustain its systems. And in those 4 years, it rewrote our understanding of Mars from the inside out. Mars has regions of volcanic activity, although no currently active eruptions have been confirmed with certainty. The planet is thought to be volcanically dormant rather than dead. Its mantle still warm enough to produce volcanism, but its thick, rigid crust suppressing the eruptions that a thinner or more fractured crust would allow more freely. Evidence of geologically recent volcanic activity has been found in lava flows that appear to be only a few million years old, a blink in geological time, suggesting that Mars may have had volcanic eruptions far more recently than previously believed. If Mars is not entirely volcanically dead, then there may be places where geothermal heat is still warming the subsurface, where water ice might melt into liquid, where the warm and wet conditions that microbial life requires might still persist, hidden deep below the frozen surface in pockets of warmth that the planet has not yet surrendered. The Tharsis Volcanic Plateau is a massive elevated region on Mars, roughly 3,000 miles across and several miles above the average Martian elevation, home to some of the largest volcanoes in the solar system, including Olympus Mons and the 3 great shield volcanoes of Tharsis Montes. The entire plateau is the result of billions of years of volcanic activity pouring lava upward through the Martian crust, building the surface layer by layer into an elevated bulge so enormous that it actually affects the rotation of the planet itself. Mars's geographic poles are offset from its rotation axis, partly because of the sheer mass of Tharsis pulling on the planet's spin. It is, in some ways, the defining feature of Mars, the great swell of ancient volcanic ambition that rose from the planet's interior and left the landscape forever shaped by what came up from below. Mars's low gravity and thick, mostly stationary crust allowed its volcanoes to grow to extraordinary heights that no volcano on Earth could match. Because on Earth, the tectonic plates move continuously, carrying volcanic hotspots across the surface and creating chains of smaller volcanoes like the Hawaiian island chain. On Mars, the crust does not move significantly. A single volcanic hotspot stays in place, and lava pours upward through the same conduit for billions of years, building the volcano higher and higher and higher without the movement that would disperse that material into a chain. Olympus Mons is the result of this patience. Not a fast or dramatic event, but a slow, almost unimaginable accumulation of lava over geological time. A mountain built one layer at a time, reaching toward a sky it has long since left behind. The average surface pressure on Mars is about 0.6% of Earth's atmospheric pressure, so low that liquid water cannot exist stably on the surface today. At this pressure, water does not behave the way it does on Earth, where it transitions through the familiar sequence of ice to liquid to vapor as temperature rises. On Mars, water at the surface skips the liquid phase almost entirely. It either exists as ice or, when warmed, sublimates directly into vapor, evaporating without ever passing through the flowing, pooling, river-making liquid state that carved the ancient riverbeds still visible in the Martian rock. This pressure threshold is called the triple point of water, and Mars sits just below it, so close to the conditions that would allow liquid water and yet just beyond. It is one of the most poignant distances in the solar system, a world that came so near to remaining wet and remained instead just dry enough. Mars was named by the Romans after their god of war, Martius, the red and powerful deity associated with conflict, valor, and the blood of battle, because the planet's blood-red color in the night sky suggested to the ancient observers something fierce and martial. The Romans were not the first to notice this. Many ancient cultures independently associated the red wandering star with war and fire and divine violence. There is something both ironic and beautiful about the fact that a planet named for the most combative of human impulses is also a place where we now project our deepest hopes for new beginnings, for human settlement, for the continuation of our species beyond this single fragile world. Mars, the god of war, has become in our imagination a world of possibility, of peace even, of the kind of beginning that has nothing to do with ending other things. Ancient Egyptians called Mars Her-Desher, which means the Red One, a name both simple and direct, stripping away the mythology and seeing only the color, only the visible quality that has always made Mars unmistakable among the other lights in the sky. The Egyptians were meticulous observers of the sky. building entire aspects of their architecture and religion around the movements of celestial objects. And Mars, that wandering red star, was noted carefully in their records, its cycles tracked and incorporated into their understanding of the cosmos. To call it simply the Red One suggests a relationship with it that was perhaps less fearful and more observational, an acknowledgement of what the planet actually is, just as it is, without the weight of war and bloodshed that other cultures draped over its red light. Her Desha, the Red One, a name that feels somehow closer to a truth. The Babylonians named Mars Nergal, their god of fire, destruction, and the underworld, a deity associated with plague, death, and the scorching heat of summer. In Babylonian cosmology, Nergal was a complex figure, fearsome but also necessary, associated with the transformative power of fire that destroys in order to make space for what comes next. The Babylonians were among the most sophisticated astronomical observers of the ancient world, and their records of planetary movements, including Mars, were so precise that modern astronomers still study them. To name Mars after Nergal was to give it a kind of respect, a recognition that this red wanderer in the sky was powerful and not to be taken lightly. The same planet that we now send rovers to explore was once understood as the eye of a god, watching from the sky with the weight of fire and ending in its gaze. Ancient Greek astronomers referred to Mars as Ares, the Greek god of war, son of Zeus and Hera, a fierce and tumultuous deity less refined than his Roman counterpart Mars, more raw, more violent, more unpredictable. Ares was not a popular god in Greek culture. He was respected for his power but rarely celebrated the way Athena, goddess of strategic wisdom, was celebrated. And yet Ares lent his name to the most dramatic object in the wandering sky, the Red One, the bright and bloody one, the planet that moved in patterns the Greeks were determined to understand. In modern usage, Ares lives on in the word Aryan, sometimes used as an alternative adjective for things pertaining to Mars, and in the name of NASA's Ares rocket program, and in the fictional colonist Mark Watney's improvised designation for his own attempts to survive a world that has never been easily survived. Mars has fascinated astronomers for thousands of years, from ancient Mesopotamian skywatchers recording its positions on clay tablets, to medieval Islamic astronomers refining the calculations of its orbit, to Renaissance scholars like Tycho Brahe, whose precise naked-eye measurements of Mars gave Johannes Kepler the data he needed to discover that planets move in ellipses rather than perfect circles. The history of astronomy is in many ways the history of humanity's relationship with Mars, the planet whose irregular motion was difficult to explain and whose resolution required our greatest minds to rethink the very structure of the solar system. Every time we thought we understood the sky, Mars asked a harder question. Every time we answered that question, it asked another. And so the conversation has gone across thousands of years between the red planet and the species that will not stop looking up at it. In 1877, Italian astronomer Giovanni Schiaparelli observed what he described as canali on the surface of Mars, channels or grooves in the Martian surface that he mapped and named with careful detail. The word canali in Italian means simply channels, which can refer to natural formations. But when the word was translated into English, it became canals, and a canal is not a natural thing. A canal is built. And so the idea was born, half by translation error and half by the hungry imagination of a species that has always wanted to know it is not alone, that Mars was home to a civilization capable of engineering works visible from Earth. The canals were not real. They were an optical illusion created by the human brain's tendency to connect scattered features into lines, but the idea they sparked burned for decades before it was finally extinguished by the camera's honest eye. Percival Lowell was an American astronomer and wealthy businessman who, in the late 1800s, built an observatory in Flagstaff, Arizona, the Lowell Observatory, specifically to study Mars and pursue his conviction that the planet was home to an intelligent civilization in the process of dying, desperately building canals to carry polar ice water to their drying equatorial cities. Lowell wrote books about this. He gave lectures. He charted the canals he believed he saw. And for a time, his Martian civilization was discussed seriously in educated circles as a genuine possibility. Lowell was wrong about Mars, but his observatory, still standing in Flagstaff today, became one of the great institutions of American astronomy. It was the Lowell Observatory where, in 1930, Clyde Tombaugh discovered Pluto. And it was Lowell's passionate, misguided love for Mars that helped kindle a century of public fascination with the red planet that has never entirely cooled. H.G. Wells's novel, The War of the Worlds, published in 1898, drew inspiration from the Canal controversy and the growing popular belief in a dying Martian civilization, but Wells inverted the premise. Rather than imagining Martians peacefully engineering their survival, he imagined them looking at Earth's greener, wetter, more hospitable environment and deciding to take it. The Martians of Wells's novel arrive in heat ray-wielding machines, devastating southern England before being defeated not by human ingenuity, but by the smallest of Earth's inhabitants, bacteria to which the Martians have no immunity. It was one of the first great science fiction novels, and it asked a question that still echoes: if there is life out there, and it is looking at us, what does it want? Wells's answer was uncomfortable, but it gave birth to a genre and a way of imagining the universe that we have never entirely let go. On October 30th, 1938, Orson Welles and the Mercury Theatre on the Air broadcast a radio dramatization of H.G. Wells's The War of the Worlds, and a portion of the listening audience, tuning in late or misinterpreting the format, believed they were hearing an actual news broadcast of a Martian invasion of New Jersey. The degree of panic that followed has been debated and perhaps exaggerated by history, but the event remains one of the most remarkable demonstrations of the power of narrative and the human capacity for belief. People were afraid, really afraid. Not because Mars had actually sent anything toward Earth, but because the story was told so convincingly that the membrane between fiction and reality briefly dissolved, and in that dissolution, the fear that has always lived beneath our fascination with the red planet. What if something is watching us back? Surfaced for a moment and looked out through open, terrified eyes. Mars remains one of the most depicted planets in all of science fiction, in books, films, television series, video games, and the broader cultural imagination of the 20th and 21st centuries. From Edgar Rice Burroughs' Barsoom novels to Ray Bradbury's The Martian Chronicles to Kim Stanley Robinson's Red Mars trilogy to Andy Weir's The Martian, writers have returned again and again to the red planet as a canvas for exploring what it means to be human in an inhuman place, to survive where survival was not intended, to build where nothing has ever been built before. Each generation has brought its own Mars to life, colored by the science of its time, the fears of its moment, the particular shape of its longing. And through all of it, the real Mars has been turning quietly in the dark, indifferent to the stories we tell about it, beautiful and cold and waiting, as it always has, for whatever comes next. NASA has outlined plans for a crewed mission to Mars, with current projections targeting the 2030s or 2040s as a potential time frame for sending human beings to the Martian surface for the first time. The complexity of such a mission is almost incomprehensible in its scope. Designing spacecraft that can carry humans safely through the radiation of interplanetary space, engineering life support systems that can function flawlessly for years, landing heavy cargo and crew on a planet with a thin atmosphere ill-suited to parachutes alone, keeping human beings healthy in low gravity for months at a stretch, and doing all of this while keeping the crew connected to Earth across a communication delay that can stretch to over 20 minutes each way. None of these problems are unsolvable. All of them are being worked on right now by thousands of engineers and scientists who have made the dream of Mars their life's work, who carry it with them every day like something precious and still to be given. SpaceX's Starship rocket, the largest and most powerful launch vehicle ever built, is being developed with the explicit goal of making humanity a multiplanetary species, with Mars colonization as the central, defining ambition of the program. Starship is designed to be fully reusable, capable of carrying 100 metric tons of cargo or a large number of crew to Mars on a single mission, and capable of being refueled in orbit so that it can make the long journey with the propellant margins that Mars's distance demands. The vision that accompanies Starship is audacious beyond the usual scale of aerospace ambition. Not just a mission to Mars, not just a flag and footprints, but a self-sustaining city, a new branch of humanity, a backup for everything Earth holds. It is a vision that may take generations to realize, or it may come sooner than anyone currently believes. The history of aerospace has always been a story of things arriving sooner than seemed possible. A one-way trip to Mars currently takes between 6 and 9 months, depending on the alignment of Earth and Mars in their orbits around the Sun and the trajectory chosen for the journey, with faster trajectories requiring more fuel and slower ones using the orbital mechanics of the solar system more efficiently. 6 to 9 months is a long time to be inside a spacecraft. It is long enough for muscles to weaken without gravity to work against, for bones to lose density, for the monotony of a closed environment to press against the psychological health of the crew in ways that earthbound training can only partially prepare for, and during those months the crew will be exposed to radiation levels many times higher than what they would experience on Earth's surface. The journey to Mars is not a casual trip. It is an act of profound commitment, a half year of irreversibility, of falling through the dark toward a destination that grows slowly larger in the windows. Earth and Mars come closest to each other roughly every 26 months during a period called opposition, when the two planets align on the same side of the Sun and the distance between them reaches its minimum. At opposition, Mars is at its brightest in Earth's night sky, visible to the naked eye as a brilliant, rust-colored point of light that outshines everything except Venus, Jupiter, and occasionally Saturn. Not all oppositions are equal. Because Mars has an elliptical orbit, the closest approaches, called perihelic oppositions, bring the planets within roughly 34 million miles of each other, while more distant oppositions leave them separated by over 60 million miles. The 2003 opposition brought Mars closer to Earth than it had been in nearly 60,000 years, closer than at any point during all of recorded human history. The most favorable launch windows for missions to Mars occur approximately every 26 months, aligned with the orbital geometry that minimizes travel time and fuel requirements. These windows are not arbitrary conveniences. They are determined by the relative positions of Earth and Mars in their orbits and the mathematics of the Hohmann transfer orbit, the most fuel-efficient trajectory between two planets. Miss a launch window and you wait 2 years for the next one. This cadence has shaped every Mars mission in history and will shape everyone in the future. A rhythm imposed not by human planning, but by the orbital clockwork of the solar system itself, indifferent and precise, offering its windows on its own schedule and closing them again whether humanity is ready or not. Terraforming Mars, the theoretical process of altering the planet's environment to make it more hospitable for Earth life, including human beings without spacesuits, has been theorized and debated for decades, but remains far beyond the reach of current technology, requiring engineering at a planetary scale that is difficult even to fully imagine, let alone execute. The challenges are extraordinary: thickening the atmosphere, warming the planet enough for liquid water to persist, generating or protecting an ozone layer against ultraviolet radiation, perhaps even restarting a magnetic field. None of these tasks can be accomplished by any technology that currently exists or that could realistically be developed within any near-term timeframe. Terraforming is a project that, if ever undertaken, would unfold across centuries or millennia, a gift given to descendants not yet born, from ancestors who started something they knew they would never see completed. One proposed early step in the long process of making Mars more hospitable is the release of greenhouse gases into the thin Martian atmosphere, gases that would trap heat and gradually warm the planet, thickening the atmosphere as sublimating ice added carbon dioxide and raising temperatures toward the point where liquid water might persist in some regions. The idea mirrors, uncomfortably for some, the process of climate change happening on Earth, except deliberately and in a place where warming is desperately desired rather than urgently to be avoided. Scientists have proposed various means of warming Mars: large orbital mirrors concentrating sunlight on the poles, factories producing powerful greenhouse gases, even redirecting asteroids to impact and release heat. Each method carries its own engineering challenges, its own timescales, its own ethical questions about the right of any species to reshape another world so fundamentally and so permanently. Astronauts on Mars would need pressurized suits and enclosed habitats to survive the Martian environment, not just for warmth, but because the atmospheric pressure is far too low for the human body to function, because the air is unbreathable, and because radiation levels on the surface would be dangerous without shielding over extended periods. The suits would need to be more sophisticated than current spacewalking suits, more flexible, more durable, capable of being donned and doffed quickly and frequently for daily excursions, designed for work rather than just survival. The habitats would likely be partially buried under the Martian regolith, the soil and loose rock of the surface, which would provide both thermal insulation and radiation shielding without requiring massive amounts of material to be brought from Earth. Mars itself, piled up around and over human structures, would become a kind of shelter, the planet protecting those who came to explore it in the only way it knows how. Radiation exposure would be one of the greatest health challenges facing astronauts on a mission to Mars, both during the 6 to 9 month transit through interplanetary space, where the protection of Earth's magnetosphere is absent, and on the Martian surface, where the thin atmosphere and absent global magnetic field allow far more radiation to reach the ground than on Earth. The radiation comes from two main sources: galactic cosmic rays, which are high-energy particles originating from beyond our solar system and are nearly impossible to shield against entirely, and solar energetic particles from solar flares and coronal mass ejections, which can deliver intense bursts of radiation over hours to days. Estimates suggest that a round-trip Mars mission could expose crew members to radiation doses equivalent to many times the lifetime limits set for career astronauts on Earth. Finding ways to protect human biology from this radiation, through shielding, through medicine, through biology itself, is one of the central unsolved problems of deep space exploration. The Perseverance rover carried aboard it an instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which successfully produced oxygen from the carbon dioxide of the Martian atmosphere for the first time in April 2021, a technological demonstration that was as small in scale as it was enormous in implication. MOXIE produced only a few grams of oxygen at a time, not enough to breathe, not enough for a rocket engine, but the proof of concept it established is the beginning of a vision where future missions to Mars bring the tools to produce their own oxygen locally rather than carrying it from Earth. Oxygen for breathing, oxygen for rocket propellant, oxygen that Mars itself can provide, drawn from the very carbon dioxide that the planet exhales with every Martian breath. A machine the size of a car battery doing something the size of a dream. Valles Marineris is the longest canyon system in the solar system, stretching roughly 2,500 miles along the Martian equator, nearly as wide as the entire contiguous United States from coast to coast. It is so vast that it would be impossible to stand at one end and comprehend where the other end is. It would be impossible even to stand at the rim in most places and see across to the other side. The canyon is simply too wide. From space, it looks like a wound in the planet's surface, a great scar left by the stretching and pulling of a crust that once moved in ways it no longer moves. And yet, there is nothing mournful about Valles Marineris from above. It is magnificent. It is one of the most beautiful geological features in the solar system, a river of stone and shadow several miles deep, carved not by water but by the slow, irresistible shifting of a world. Sunsets on Mars are blue, a soft, aching blue that pools around the small disk of the setting sun as it descends toward the horizon, a color that on Earth we associate with morning, with clear skies, with the kind of day that is just beginning. On Mars, blue is how the day ends. The fine dust particles in the Martian atmosphere scatter the red wavelengths away at low sun angles, allowing the blue light to reach the observer's eye more directly, reversing the warm palette of Earth sunsets into something cooler and more alien. Every camera we have placed on Mars has eventually photographed a Martian sunset, and every photograph carries the same feeling, something beautiful that cannot quite be named, a color that belongs to a sky no human eye has ever watched in person. Something that is waiting, perhaps, for the first person to stand there in the actual moment of it and simply breathe and watch the blue light fall. The dust on Mars is so extraordinarily fine, individual particles measuring only a few micrometers across, smaller than a human red blood cell, that once it is lifted into the thin Martian atmosphere, it can remain suspended for months, drifting on the gentle circulation of winds that carry it around the globe in vast, slow curtains of reddish haze. This dust has affected every mission that has ever landed on the Martian surface. It has settled on solar panels and dimmed them. It has coated camera lenses. It has changed the color of the sky from day to day as its concentration varies. Rovers have encountered dust so thick they could not see more than a short distance ahead. And yet the dust is also what makes Mars beautiful. It is what colors the sky those warm amber and butterscotch shades. what gives the Martian horizon its particular softness, what makes the blue of the sunset possible. The thing that challenges life on Mars is also the thing that makes it, in its own way, a world of terrible and quiet beauty. Snow falls on Mars, but it is not the water snow of a winter storm on Earth. Near the Martian poles in winter, the temperature drops low enough that carbon dioxide freezes directly out of the atmosphere and falls as dry ice snow, settling on the polar caps in layers that can be several feet thick and giving the polar regions of Mars a white, glittering quality that no visitor has yet stood beneath to feel falling on their face. Scientists confirmed the existence of Martian carbon dioxide snow through observations from the Mars Reconnaissance Orbiter, and the discovery carried the particular quality that all the best scientific discoveries carry. Not surprise exactly, but recognition, the feeling that the universe has confirmed something you almost suspected, showing you once more that it is stranger and richer than your imagination had yet managed to build. Mars has clouds, wispy, ethereal formations of water ice crystals that drift over the great volcanoes and settle into the valleys and collect along the edge of the polar ice caps in formations that, from orbit, look hauntingly familiar to the weather patterns of Earth. The Mars Climate Sounder and various cameras aboard orbiters have photographed Martian clouds in extraordinary detail. Long, thin, cirrus-type clouds catching the low Martian sunlight above the volcanic peaks of the Tharsis Plateau, morning fog gathering in Valles Marineris as night temperatures drop, and occasional cloud formations that develop and dissipate like weather that almost might have been. That Mars has clouds at all, that its thin, cold carbon dioxide atmosphere is not too sparse even for water ice to occasionally crystallize and drift, is one of the small, persistent miracles of the planet. A world of thin air and frozen ground that still, somehow, makes clouds. The Perseverance rover carried to Mars a small swatch of muslin fabric from the wing of the Wright brothers' original 1903 flyer, the airplane that made the first powered, controlled flight in human history at Kitty Hawk, North Carolina, on a cold December morning 120 years ago. The fabric made the journey to Mars tucked beneath the belly of the Ingenuity helicopter, and when Ingenuity made its first powered flight on April 19, 2021, that thread of muslin from Kitty Hawk was there, connecting in a single, quiet, physical object the first moment humanity left the ground on Earth and the first moment a human-made machine left the ground on another world. 117 years separate those two events. The same distance that felt so vast when the Wright brothers stood on the beach at Kitty Hawk, the distance between impossible and done, was bridged again on a world millions of miles away by a helicopter the size of a tissue box. Mars has what are called recurring slope lineae, dark, narrow streaks that appear and grow on steep slopes during the warmer Martian seasons and fade in colder months, repeating year after year with a regularity that once seemed to suggest the presence of flowing briny water just beneath the surface. When they were first described in 2011, the excitement was immediate and enormous. Seasonally recurring features on Mars that behaved the way water-saturated material behaves, growing downslope as temperatures warmed, darkening as they extended. For a time, recurring slope lineae were among the strongest candidates for active liquid water on the present-day Martian surface. But more recent observations from the Mars Reconnaissance Orbiter have pointed toward a different explanation. Granular flows, dry sand and dust sliding slowly downhill in the warmer temperatures, darkening the slope as they go, with no liquid involved. The mystery did not resolve into life, but it resolved into understanding, which is its own kind of beautiful. On April 19, 2021, a small helicopter named Ingenuity became the first powered aircraft to achieve flight on another planet. Lifting off from the floor of Jezero crater on Mars and hovering briefly in the thin Martian air before settling back to the ground in a moment that was, by any measure, one of the most extraordinary things our species has ever done. The atmosphere on Mars is so thin that to fly in it requires rotor blades spinning at roughly 2,500 revolutions per minute. 5 times faster than helicopter blades need to spin on Earth, just to generate enough lift in air that is only about 1% the density of Earth's atmosphere. Ingenuity was only ever supposed to demonstrate that flight on Mars was possible. It was a technology demonstration, not a scientific mission. It proved far more than anyone quite expected, and then it kept going. Ingenuity was originally designed to fly 5 times over the course of 30 days. It flew over 70 times before its mission came to an end in January 2024, when one of its rotor blades was damaged during a landing and it could no longer fly. Over the course of those 70-plus flights, Ingenuity traveled more than 11 miles across the Martian surface, reached altitudes of up to 79 feet, and served as an aerial scout for the Perseverance rover, looking ahead along the rover's planned route, identifying interesting geological features and performing reconnaissance that no ground-based rover could have done. It outlasted its design life by a factor of more than 14. It became, in the years of its operation, something that no one had quite planned for it to become. Not a demonstration, but a companion, a small and faithful presence in the Martian sky, doing more than anyone had dared to ask of it, and doing it with, in every photograph, a kind of joyful relentlessness. In May 2021, China became the second country in history to successfully operate a rover on the surface of Mars when the Zhurong rover, part of the Tianwen-1 mission, landed on Utopia Planitia, a vast northern plains region of Mars, and began its surface operations. Zhurong was named after the god of fire in Chinese mythology, carrying its own cultural thread into the tapestry of Mars exploration. The Soviet Union's Mars 3 lander had technically achieved the first soft landing on Mars in December 1971, but transmitted data for only about 20 seconds before going silent, a brief, fragile contact with the Martian surface, a whisper of presence rather than a mission. China's Zhurong was different. It drove, it collected data, it operated for many months. Mars, which had for decades been primarily an American destination, became in 2021 something more. A world that humanity, in more than one of its expressions, had reached out and touched. Despite being named for the god of war, Mars, rust-colored, quiet and vast, feels less like a battlefield and more like a dream waiting to be remembered. It is a world of blue sunsets and iron dust and ancient riverbeds that have not known water for 3 billion years. It has 2 small moons with fearsome names that circle it in the patient dark. It has a volcano tall enough to breach the stratosphere and a canyon wide enough to contain a continent. It has been turning quietly on its axis, tilting through its long seasons, holding its frozen water underground and its secrets in the stone, for longer than our planet has had complex life. And it is waiting, not urgently, not impatiently, but with the deep patience of stone and cold and the particular stillness of a place that has never been visited in person but has been loved in the way we love things that are beautiful and distant and not yet entirely understood by every human being who has ever looked up on a clear night and noticed the red light burning quietly among the stars. And so Mars turns, out there in the dark, as it has always turned, as it will turn long after this moment has passed into memory. You have heard its stories now, the blue of its sunsets, the silence of its ancient rivers, the small bright point of Deimos drifting across a sky the color of warm dust, the ice that holds the memory of oceans, the rovers that crossed its plains and gave everything they had and went quiet in the way that beautiful things sometimes go quiet, not with an ending, but with a stillness that says, I was here, and it mattered, and the stone remembers. Let all of this settle softly into you now. Let Mars drift back to its place among the stars, that small red ember in the deep sky, patient and extraordinary and waiting. And let yourself drift too, into the quiet, into the warmth, into the long, unhurried dark where all things rest. Sleep well. The universe is still turning. Mars is still there. And everything is, for now, exactly as still and as beautiful as it needs to be.